Hi, everyone. Thank you for coming to Black Hat 2015. A couple quick announcements. There will be a reception tonight in the Business Hall at 5:30 p.m. The Business Hall is located in Shoreline A room. Second item is the Pony Awards will take place tonight in the Mandalay Bay B, C, and D, now at 6:30. So if you heard earlier that it was 6, that has changed to 6:30-ish. And that said, you are in Lagoon K for the session Faux Disk Encryption, Realities of Secure Storage on Mobile Devices with Daniel Meyer and Drew Suarez. If everyone could, please make sure you silence your cell phone and enjoy the session.
Thank you. Hey, good afternoon. Thank you, everybody, for coming to our talk about faux disk encryption and the realities on secure storage on mobile devices. I'm Daniel. I'm a principal security consultant with NCC Group, formerly Matasano Security. We are a security consultancy, and we also do software escrow and domain services, among like a number of other services. Our headquarters are in the UK, but we have a bunch of offices around the US. I'm more of an iOS kind of guy, so the sections I will be talking about will be more on iOS. I've developed this pen testing tool called IDB. Maybe some of you have heard of it.
And I'm Drew Suarez, also a security consultant with the NCC Group. I'm also a member of the open source wing of the CyanogenMod project, helping bring up new devices and also writing the building and exploit documentation for the wiki for them.
Right, before we get started, a brief outline here. The introduction will be giving some background on what are the challenges in mobile devices compared to like traditional client-server settings to secure data. Then we will talk in depth about which mechanisms iOS provides for that, and then do a similar thing for Android and talk about the challenges there, which are more particular, and show you also a new attack in a way we have come up with to bypass full disk encryption on some Android devices. And then we will summarize this and try to give an outlook what we see where the challenges are in the industry and what we would like to happen in the future. So what makes mobile special? So if you have a traditional client-server setting, all the data is stored on a server and you can enforce tight controls on it. You have users logging in and you have authentication and things like that. But if you have a mobile device, it turns out that most users are not using the device or accessing data via the Safari or any kind of embedded browser. What they actually do is they use mostly apps on the device. And those apps are storing data locally on the device, and it's much harder to access or to secure that data, rather. And why is that a problem? Well, if you look at these statistics here, in the US, in 2013 alone, there were 1.4 million phones lost and 3.1 million phones stolen. So there is definitely a need to secure this data which is stored on the device to protect it in these kind of circumstances. But at the same time, we need data on the device. We cannot just prevent users from storing something there. So we have this accessibility problem of having data on the device and needing to protect it. And this can be data, or it can be usernames and passwords, or any kind of other credentials on the device. And then on top of all that, we have to reconcile those two concepts while still making it usable. So if we build a secure system where nobody can get to the data or users are hindered by it, they will either not use it or will just try to bypass all the controls. And they will just think whatever we are imposing on them is just as random as what's in this comic here.
All right, thanks. So I think it goes without saying there's no such thing as absolute security, but it helps to look at who you're concerned about with the data on your device and what data you want to protect. So there's things like remote attackers, somebody who is trying to remotely access your device. The coffee shop attacker, which is somebody who sets up a rogue AP in a public place trying to get connections, or perhaps they've hacked a public Wi-Fi. There's your casual thief who really doesn't care too much about the data on your device. They just want to flip the hardware and make a quick buck. Then there's the more targeted attacks, somebody who's specifically coming directly for you for a particular reason. And then we have nation states who have a lot more time, money, and resources to dedicate to something like that. So if we plot those out on a graph of the sophistication of the attack and the effort involved, we can kind of place the things we just talked about with the casual thief being very unsophisticated and requiring very little effort to snatch something from you, all the way up to the nation state, which would require more sophistication, more effort on their part. So Daniel's going to talk a little bit about mobile data security. Actually, I'm going to hand that over to Daniel.
Right, so mobile data security, One word first, because this is kind of what always comes up when people think about mobile devices. Full disk encryption. Everybody says, oh yeah, Android has full disk encryption, iOS has, so our data is secure on there. So the one thing to keep in mind, it encrypts and decrypts data transparently for you whenever the device is turned on. So you don't get any protection when the device is actually running. So the only way to protect it would be to have the device turned off all the times. And while there may be scenarios where you purposefully turn your device off to protect it at that point, this may not be sufficient. We need more fine-grained control in the way that we want to have our devices on and still be able to protect data. So we need some more fine-grained control to control access better than device on and device off. And with that, let's look at what kind of facilities iOS has for that. So the first distinct advantage it has over Android, as well as, to some extent, Microsoft, is that they produce the hardware and the software. So they can build hardware features and have good software support for them, and they can build hardware support for certain software features. And that allows them to start security on the device really from the boot. So we have a ROM which has a CA in there, and we can verify that the bootloader, the kernel, and everything following there is actually signed by that CA, and we know that it's trusted and hasn't been modified by an attacker. And then moreover, once we look at the operating system itself, all updates are signed by Apple as well. So if you install a new update for iOS, you have the guarantee that it's an authentic product and it would not run otherwise on the device. Similarly, there's no downgrades allowed. This, whatever reason it may have why this is implemented, but the good thing is that if you have a security patch to an update, you cannot revert from that, so you cannot get less protected basically than the latest release. And lastly, we have app signing, which is dealing with anything running on the operating system. And all apps have to be signed by Apple. When you download it from the App Store, it is signed by some certificate signed by Apple. And that actually goes all the way down to the code level. So if you run code, every code piece is checked when it's being executed. And then finally, if you jailbreak your device, which is fairly common in the research community at least, you lose a lot of these protections. So from a securing yourself standpoint, it's not really recommendable to jailbreak your device, and we'll talk about that in a bit. So let's talk about how we implement encryption using this platform. The first thing is, in order to protect something on the device, if somebody steals it from you, we have to have something which is not on the device, because if somebody gets it, they can't just read anything off the device, and if there would be an encryption key which we're using, they could just read the encryption key and decrypt any data. So that's where the device passcode comes in. So whenever you type in your passcode on an iOS device, it will use PBKDF2 to derive an encryption key from that and use that to wrap data which you choose to protect under this class. And then the key is being wiped every time you lock the device. So while the device is locked, this data is not accessible. But the problem is that a lot of studies have shown users are really bad at choosing strong passcodes because it hinders their usability. And one could just copy the data off the device and then perform an offline brute force attack. So for that, to prevent that, we would need to have some sort of tie into the hardware or some hardware root of trust. So on iOS devices, we have the secure enclave, which is holding the encryption keys inside of it. And we can only ask it to perform a decryption operation for us, giving additional passcode information. But we cannot read that key off the device. So if somebody were to brute force something, they will never get that piece of the key, so they would need to run that attack on the device, which is much slower. So we can enforce brute force controls, and we can also wipe data from the device if there's too many failed attempts. So let's see how this incorporates into the general structure on how data or files are encrypted on iOS. So this graph starts off here in the lower right. You see the file which is protected, and every file has a file key which is associated with it, and it's just stored on the file system. And then we tie this into the hardware by having the hardware key with which we protect the so-called file system key, which then protects the file key. So with that, we basically tie this file to the device, so any decryption operation with that file has to happen on the device. But the problem is, if you steal the device or get physical access to it, you can still simply perform that operation on the device. In order to prevent that, we then have the passcode, as I already mentioned. And the passcode is used to derive another key, and then that key is combined with the hardware key in some manner to derive so-called class keys, which I will talk about in a second. And then those, together with the file system key, are used to wrap that file key, which you see in the lower right. You may wonder why we even need the file system key in that case. The good thing about this is if you want to remotely wipe your device or you want to delete the data on it, you can just delete that key and no data on the file system will be accessible anymore. So let's look at the class keys. So the goal for this whole mechanism was to have more fine-grained control over your data. So if we split these up, we have NS5 protection none, which is only tied into the hardware key, and then we have the other two, which are also tied into the passcode. So if you use the one which is called NS file protection complete until first user authentication, files will be protected from the time you turn on your device until the first time the user unlocks the device. And then it will be accessible from then on forth. That's very similar to how full disk encryption on Android or on Linux works. The other one, the protection class complete, ties in fully with the passcode, and the key will be wiped whenever you lock the device. So that kind of sums up the brief overview of like the different functionality you have available to protect files on iOS. The other facility which is there is the iOS keychain. And that's internally, it's just a SQLite database which lives on the file system. And in there, we have different entries which are protected using different keys. So you have each entry in the SQLite database protected using a key which gives you the different guarantees we already talked about. It's very similar. The main criticism I have for this is that if you uninstall an application, it will not delete the data. There's not even a way to hook the uninstall process and delete data. So you may uninstall an application which stored something sensitive in there, and a year later somebody can get your phone and the data will still be in the keychain. So as I mentioned, the keychain protections are very similar to the ones we talked about for the file system. We have the none class, which is equivalent to keychain accessible always. Then we have after first unlock, which is the same as I talked about before, and then when unlocked. The only thing which is different is since iOS 8, there is a new option here, which is called when passcode set. And the common problem which came up is that if you don't control your devices, like you have an MDM solution in a corporation, you cannot enforce that users have passcode set on the device. So if you store data in the keychain, they may actually not be protected properly because the user didn't choose to have a passcode. So this, if you store data with when passcode set, it will actually only store the data if there's a passcode on the device, and it will remove the data when the user removes the passcode and protects that. So you might wonder why we need all these different classes. And this comes back to having this granular control over your data and protecting it for the right circumstances. So there's some data which just needs to be accessible always. You want to turn your phone on and you want to be able to receive phone calls, you want to be able to receive messages, so all keys and data which is related to that needs to be always accessible to the device. But there are other things like wireless credentials, email credentials, and it's acceptable for you to first unlock your device at least once before you can use those services. So we can protect those more and have the user at least type in the passcode once in order to use them. And then finally, things like Safari passwords or backup credentials you will not need when the device is locked because you will not use Safari when the device is locked. So you can protect them with this even stronger protection class and have them only accessible when the device is unlocked. So following this line about usability, one important thing is that if you always need to unlock your device in order to use it, you have to type in a passcode. So the Touch ID is a feature which was introduced in iOS, and I think it has been in the beginning pretty much misunderstood or misinterpreted because the big news was, oh, it can be bypassed. That's true, but how many of you are actually concerned somebody going to a bar and lifting your fingerprint to access your particular data versus somebody being able to mass compromise people? So there's like this trade-off between which attacker you're trying to protect against. And Touch ID protects the passcode, basically. So you type in the passcode the very first time you start the device. It's stored in the secure enclave, and then it will only be released whenever the Touch ID receives a valid fingerprint. And then the encryption is still based on the passcode itself. And besides device unlock, it also is tied into two mechanisms which are exposed to the developers. The first one is user presence for the keychain. And that basically takes the granular control one step further. It's not only when the device is unlocked is that data accessible, but it's accessible whenever it's protected until you actually try to read it. So you try to read a keychain item, and you will get a dialog popping up, say, please swipe your finger or enter your passcode. Very similarly, local authentication, but this is an OS-level API. It's not tied into encryption for the keychain. And it basically just allows your application to ask the operating system to say, hey, is the right person there? And if so, it will allow you to will allow the user to, it will prompt the user and you put your fingerprint on it and it will tell the application, yes, the user was there. But if you jailbreak the device and you get control over the operating system, you can just modify those API calls and can just tell any application, yeah, the user was there. So the control with the keychain is significantly stronger than just having an OS-level API for that. So with that, what does it leave us with security threats for iOS? So the good thing is that since the stack is pretty protected overall, you need to bypass some of the existing controls in order to gain significant access to the device. So if you jailbreak a device and you find a flaw which allows you to bypass signature checking and jailbreak it, you can get access to everything which is not protected under the passcode. Because if you don't know that, you cannot derive the encryption key for that, and you cannot gain access to that data. Other things which may be a threat are just malicious applications which are asking for a lot of permissions and trying to access more of your data than they really should be. And then evil mate-style attacks, which we will be talking about in a bit in more detail. And they're tying into jailbreaking and modifying some parts of the operating system. And we will talk about that in more detail after the Android section. And with that, I'm going to hand it off to Drew to talk about how Android compares to this.
All right, thanks, Daniel. So let's look at how Android approaches these same challenges that we just saw in iOS. So this is a helpful graph to see the evolution of the introduction of new security features into Android. And we can see as time has gone on, we've gotten more and more advanced things. I've highlighted the ones in blue that pertain specifically to secure storage, but left the others for you to look at later as well. So the ones specific to secured data storage that I find interesting are DM Verity, which is relatively new. It was introduced in Android 4.4. And this protects the system partition by taking a SHA-1 hash of each block and then building a tree on that, such that if you need to modify the system partition such that you want like a persistent root, it's going to realize that it's broken at that point and give you a nasty warning when you boot. There's also the trusted execution environment signing of the key encryption key, which I will talk about in more detail later, as well as Force Encrypt. So Force Encrypt was launched with Android 5.0 in the attempt to enable full disk encryption out of the box. Because up until that point, this was a user electable feature. So you had to go through a bunch of settings menus and say, yes, I want to encrypt my device, and go through like a half-hour painful reboot process to enable that. Unfortunately, one could speculate that Google's OEM partners weren't quite ready for that, so they quietly removed that requirement for Lollipop. So really the only devices that launched with Force Encrypt were Google's own Nexus line. So if we look at the adoption of Android as a platform, it's pretty easy to see, and everyone's heard of the fragmentation problem in Android. A lot of users are on an older version of the platform at this point. The majority of the users are not using the latest possible version. So it's interesting to compare that back to iOS and see that the majority of users are on the latest version and thus have the latest security features available to them. So why is this so important to the ecosystem? It has a very large effect on application developers who want to make their application run on all versions of the platform, but can't guarantee that they have access to the security APIs and the features that the newer versions have provided. So there's a code complexity problem in that you need to make decisions based on what version that your application's running on. And as we mentioned, access to the most secure features is not always available for everyone. And that brings us to the interesting problem of the OTA process for Android. And this is a very complex problem that I'm summarizing very quickly for you, but Google tends to provide these things pretty quickly in AOSP, in the Android open source project. But it takes a while for those actually to get out to the end user because OEMs like to customize Android and have their own brand, and so they add on all these new features. So when these things come out, it goes to the OEM level, they make their changes, and then another layer of complexity is that the carriers are involved in this as well. So the carriers need to certify the builds, they want to add in the cool NASCAR app, I guess, or whatever, to the ROM. So this makes things slower in terms of users actually receiving timely updates to their device. So we're going to briefly talk about how the Android encryption system works. This is a simplified version, and also of note, this is the Google-specific version. OEMs tend to make modifications to this, but that's sort of outside the scope of what we're going to talk about here. So a device encryption key is generated randomly when you elect to enable full disk encryption. This is based on dmcrypt, the device mapper portion of the Linux kernel. It uses AES 128 in CBC mode, along with an ESSID SHA-256 for each of these sectors, and then you encrypt the volume in this fashion. But since this is not derived from the user passcode, we need some way to have a passcode on top of that such that if you want to change your passcode, you don't have to re-encrypt your volume. So this problem is solved with what's called the key encryption key and an initialization vector. And so the key encryption key is derived from a user-supplied passcode. This wraps the device encryption key, and then that is stored encrypted in the crypto footer, which I'll get more into later. So we can see here the lock screen. This can be a PIN, pattern, or passcode. In Android 4.3 and below, this was handled by PBKDF2. After and including the KitKat release, Android 4.4, Google switched to scrypt in an attempt to reduce the brute force attacks on the PIN codes. And then finally, in Lollipop, Google introduced a new feature that allows you to sign the password key with something from the trusted execution environment that cannot be removed, such that if you want to do some sort of attack on this, you're going to need to use the device now. And this was brand new for 5.0. So referring back to the crypto footer, it's worth noting that Android's full disk encryption actually only protects one partition of the entire flash device, and that's the user data partition. This is where all user settings are stored. Anything you download is stored there. The crypto footer, which I referred to earlier, is usually carved out of this user data partition. It's 16 kilobytes at the very end of it. More modern devices, we're starting to see that there's a dedicated partition for crypto metadata. And as I mentioned, the master key or the device key is stored as encrypted by the key encryption key here. If you're familiar with Lux at all, it's a very similar idea, except it has one significant difference in that it only has one key slot. So you're only able to have one key stored. There's a lot of projects that require heavy customization of the ROM you're running, but that allow you to have a very strong boot decryption password and then also have like a passcode that's a little bit more reasonable so that you can have the very complex one and the more user-friendly one as well. But again, this is not standard and requires modification to the platform. So a word on how Android handles credential storage. The system credential store will hold things like VPN keys, Wi-Fi, asymmetric keys, either from applications or your own keys if you want. These are encrypted by a key that is derived from the user's passcode. And this can be hardware backed, which is a new security feature that a lot of devices are shipping with these days that actually lets you store the keys in hardware backing such that they can't be removed from the device. So this adds additional security for obvious reasons there. But there are some issues with the key store, namely the fact that developers can't really rely on the fact that somebody has a hardware-backed key store. So there are APIs available that you can test to see if the system you're running on has one, but again, it's inconsistent. And there have been a number of issues that have actually been fixed in Lollipop in 5.0 relating to changing the user's password will actually obliterate keys from the key store and sort of erratic behavior. So this is actually luckily improving with M. It's well documented now. There's different conditions, and we don't have the bug of changing passcodes blowing away keys. So it's an effort to make things more developer friendly. So let's talk about Google and their OEM partners here. The biggest issue here is the wild inconsistency in how many people make Android devices. One of the great things about Android is that you can run on a very budget device or the current flagship and everything in between. So it's a very accessible platform. But with that comes the downsides that you don't have all of the security guarantees across the devices. So there's things like bootloader security is wildly different. Hardware-backed crypto storage, what we just talked about. The availability of a trusted execution environment or a trust zone component. And even the boot image type varies by device. So it's a very complex system. And with different OEMs, as I said, comes different security precautions or protections, I should say. So a lot of devices have an eMMC write protection layer. So even if you are able to root the main system, you're not able to overwrite certain partitions because it'll just discard them at that level. We also have things like the boot image signature verification. So a lot of devices will verify that the boot image is signed properly, but a lot of them also won't, as we'll see coming up. And then there's also the different types of bootloaders. So there's locked, such that that's it. You're not able to modify that in any way. There's locked but unlockable, which is becoming more common from things like Sony, HTC, and the Nexus line, obviously. And this will allow you to get a token, either from the developer program or in the case of Nexus, just enable the option and then use fastboot to unlock your device. And these will responsibly erase the user data partition like you would expect. So it's a difficult problem to solve because it's challenging for Google to enforce standards on their OEM partners because they want to have their own devices, they want to do things their own way. And as Daniel mentioned earlier, Apple has a distinct advantage here because they control the entire stack from the hardware to the software. So they can make this work a lot more cohesively than Google can. So let's talk about the importance of boot security, which is a central point of our discussion here. So on the top left there, we have the bootloader, which we've marked in green as being secure because there's multiple layers of signing that happen as the different bootloaders hand off to each other. If this signing is broken, you're pretty much not going to get a boot. So we consider that to be well-rounded. And then all the way at the bottom, we have the user data partition as illustrated. The user has elected to turn on full disk encryption. They're protected at this layer. But in the middle, we have two possible vulnerable places. One with the kernel itself. As I mentioned, if there's a lack of boot signing verification, you can, in a lot of cases, overwrite this with something that you control. And similarly, the system partition, which is where the main operating system lives, is not encrypted. So in cases where there's no DM Verity, which is really not shipping on any devices at this moment, you can modify the system and make changes at that level. So I want to show a few examples of that. Let's talk first about download mode, or Odin mode. This is a Samsung-specific bootloader interface that ships on all of their devices. It's internally, Samsung uses a tool called Odin to interact with this, and it allows you to arbitrarily write images to the different partitions on the flash. And if you're interested in this, I would definitely recommend Heimdall. This is written by a guy called Ben Doble from Australia, and he's sort of reversed how Odin worked and made a cross-platform open source version of this tool that you can use. But based on what I said, it's clear that this is overly permissive. A user should not be able to arbitrarily overwrite certain parts of their device with user-controlled content. And most of the devices they ship have this issue. So outside of a few very select US carrier models, most notably on Verizon or now on AT&T as well, which do check the image signatures, all of the international devices and all the other ones have the ability to be interfaced with in download mode. Little kernel is a bootloader found on many Qualcomm devices, but even something that has open auditing has issues. So there's a couple CVEs related to this that would allow us to bypass image verification. This first one, they forgot to actually check the signature in a build that came out, so there's quite a few devices that let you just fast boot your own image directly, and then from there you can do all sorts of fun things. The next one is a little bit more complex, but you can forge signatures, and this uses RSA cube root attack. I would definitely recommend reading that CVE for the details on that one. It's a little complex. And the last one is relatively new. When updates are flashed with fastboot for system, it's typically a sparse bundle. They did not check the end of the bounds of where that sparse bundle ended, so people figured out it was possible to write past that boundary and potentially overwrite different parts of the internal memory. And lastly, Laugh, which is properly titled because this is a hilarious backdoor that's found on a lot of LG devices. You put it into a special mode similar to Samsung's download mode, and then you use a binary called send command, and it takes one argument, and that is the COM port of what your device is plugged into. And once you issue that command, you are dropped into a root shell, and from there you can do all sorts of interesting things as well. The unfortunate thing is that LG realized that this is probably not a great idea, and they tried to fix it, but their fix is rather incomplete. And so they decided to protect individual partitions, like block P1, P2, P3, but block 0, the root of that, is not protected. So you can use DD and seek and some clever offsets and actually overwrite the same partitions you were able to before. So users are able to impact the boot image here as well. And this was actually shipped on the Nexus 5 as well. So let's revisit the idea that Daniel brought up earlier, that full disk encryption protects when the device is turned off. We are going to demonstrate that that's not always true. And in typical InfoSec fashion in the last few years, there needs to be a cutesy logo and title for this. So we're calling our POC Rosie, the evil Android, evil maid. And in this scenario, we are exploiting permissive bootloaders. So we flash a custom boot image that we've backdoored. And this can happen in under 2 minutes, including multiple reboots. We give this device back to the user. They log in with their encryption code, and this becomes active. We have profit here. So you can do things like hook kernel cryptographic functions and grab the encryption key that way. You can exfiltrate data straight off the device, which we chose to do, or shells, anything you want. You have kernel level access at this point. So we're going to talk a little bit about how we tested and devised this idea. So the first step is to put your device into its permissive bootloader state. Then we use the tool we referenced earlier to flash our own custom recovery image. And that's sort of outside the scope of this, but I've done a lot of prior research on recovery, so I recommend if you're interested in what that is, you can reference that and learn on your own. But basically, a custom recovery provides a nice test harness. It gives you a root shell. You have access to all the unencrypted partitions as root, so you can mount file systems and make changes that way. But it also is a very handy platform for backing up essential firmware and also for flashing your own firmware and getting to a place where if you write something that doesn't boot, you can come back to recovery, fix it, and then you're good to go. So I'm going to hand it over to Daniel to talk a little bit about the next section.
So we made our own kernel, first of all, to get it backdoored. Luckily, all kernels which you get for Android devices from the OEMs are open source because the license requires them to make them open source. So you can just go to any OEM and you download this kernel source code. And then we added a kernel module, which was our backdoor, which is just opening up a UDP connection to a server we control and exfiltrates a file from the device. And obviously, we added this to menu config so that you can conveniently add our backdoor here. And then for testing purposes, all you need to do is you compile the kernel, you create a boot image, which just takes a second or so, and then we can boot into recovery and flash the boot image on the device, reboot and try it out, and if it doesn't work, we just rinse and repeat until we had our final version, which was the boot image, which is backdoored, and we knew it was working properly. And then we don't need all these steps which we just talked about. And we'll show you in the next video what it takes to actually then just attack a device and how much or how little access you need.
All right, so here we're starting with the...
I think it's playing now.
Okay. Here we're starting with the device on. This is not a requirement, as you'll see coming up, but just for demonstration's sake, we're turning the device off. At this point, we're going to start a counter for when the device is off, because the interesting scenario here is that you think you're protected when this is off. So we're going to boot into our permissive bootloader, accept the warning that custom operating systems can cause problems, obviously. We're going to connect the device via USB, and then Daniel is going to flash our backdoored kernel to the device. And you'll notice very, very quickly how fast this runs, and in just about under 23 seconds, that's it. The backdoor is active. Now the phone is booting, it's active, and Daniel will talk about what happens next when this boots up here.
Right, so in our scenario here, the device basically was off, and we just put it back where it was, and the user just picks it up again and starts using it. So the next time the user boots it up, they will just get the regular password screen where they need to enter their passcode. So this is where we're at right now. And in the meantime, on the right side, you see the console we have open running on our server, which is just a random DigitalOcean droplet somewhere on the internet, listening via netcat, just keeping it simple. And once the user unlocks it and the device takes a while to process, we will see that we can receive the data there.
Yeah, when you use your own kernel, you lose a lot of the hardware acceleration, so it takes a little while for the encryption process to happen.
So as soon as the unlock happens, the data gets dumped over there. And then we can verify that we actually got the right file. We got the account SQLite database from the device because it has at least some sensitive data in it, and it's actually not readable by the regular user. It's protected. So we can open it, we can make some queries in there and see what we have. And then the last part here, just ADBs into the ADB shell on the device and trying to access that file directly, and you can see that there's access denied. So a regular user, even on the device, couldn't get it. So that kind of proves that we're running with something which is like kernel level access. So this is, as Drew already illustrated, by giving the three examples of the different bootloaders which have been vulnerable in the past. This is possible on a number of OEM devices. But it's not really a new problem. This is known that you can do this for a while, and people use it for all kinds of purposes. And it's also not new that you can do backdooring kernels and evil mate attacks and things like that. But we feel like it's important to point out that there is actually a security implication of having permissive bootloaders, and that if you rely on full disk encryption and you don't fully protect the stack along the way, then you basically lose that guarantee which you're hoping full disk encryption can give you. Granted, this requires physical access, but it is still a flaw because people assume when it's off, it's secure. And then lastly, we should talk about that Google also actually has provided mechanisms to prevent this. So if there's facilities there which have signature verification along the way, there is DM Verity support in principle, so we can protect those things properly. It's just not implemented widely yet. And hopefully this will give people some idea that there may be actually a need for doing so in the future. So for iOS, the last point here is this exploited a bootloader which is just permissive by default. If you're able to jailbreak an iOS device, you can do obviously similar things. You can backdoor an application and you can just obtain any data, or you can just backdoor the kernel and you can exfiltrate data that way. So this is not particularly an Android thing, but the attack is just particularly simple for these kind of devices.
All right, thanks, Daniel. So this is the slide we've dubbed Drew's soapbox. So I'm an Android enthusiast. I've been doing custom Android for a while. Thanks. Worked on a lot of devices, and the platform's great and it's open and you can create custom things that are useful for you. But these things should be secured by default. Out of the box, you should have security guarantees. And so it would be really helpful if OEMs picked up on that and started to secure these things by default. And in the example we just showed, just verifying the boot image is not going to solve the problem, because you're just locking somebody out of the device that they purchased and want to do legitimate modifications to. And so we get into a scenario where more dangerous exploits have to be designed in order to gain that access back if you're just going to lock the door behind you. Which brings us into responsible bootloader unlocks. This is already happening on a lot of OEMs. Unfortunately, some carriers block this entirely, like Verizon. And this will responsibly erase the user data. So if somebody comes across your device and wants to unlock it, they're going to blow away what they're after, right? If they have an evil mindset. So having this responsible unlock is a good solution. Make the user agree to some conditions and then blow the data away. And I think we also want to see some very clearly documented guidelines of what's protected, because every device seems to have like totally different random things that they're protecting. There's no consistency. And lastly, consistency among Google's OEM partners would really help the ecosystem here. Let's decide on one cohesive bootloader solution that's audited by all parties, that isn't private and closed off and only looked at by a few people. And I think we can solve a lot of these issues that we just showed in our demo here. I'm going to hand it back to Daniel to talk about some alternatives to the platform security.
Yes, this kind of wraps up the device-specific discussion. But what do you do if you don't have a passcode set on a device and you can't enforce that? You probably heard there's a lot of app container solutions out there, such as Good or Mobile Iron, things like that. And they basically implement the same thing we already discussed in this talk. They just do it on an app level. So they're going to have a lock screen, and that lock screen will use to derive a passcode, and then all data in the app's container will be encrypted with that data. And then you can wipe the key when you background the app, and you basically build the same mechanism as we've seen before. The one downside here, or the two downsides are, is that crypto is hard, and a lot of things can go wrong. And probably most developers should not try to implement things on with basic primitives and crypto, but use libraries for that and try to keep it on a more abstract level. And then the second thing is that these kind of mechanisms are not hardware backed. So if you get somebody's app sandbox and they don't have a strong passcode or something which is easy to guess, you can still run brute force or guessing attacks offline compared to the system protections. And then something else to think about is, do we need to have data on the device? And that kind of goes into the usability discussion in here. Does data need to be on the device? Can we just leave it on a server and we get it accessed on demand? But then what do we do? Do we authenticate the user every time you need to access the data? Or do we have to store a long-lived token to access the data, and then we're kind of circling back to having to store that token somewhere? So this may or may not solve the problem depending on what your usability requirements are for your particular application and how paranoid you are about the data you're trying to protect. So where does this leave us with all what we have talked about? Well, for users, we've seen that the passcode is actually really central in all the secure storage techniques. So setting a secure passcode is really something which should be encouraged. And using something like Touch ID or anything which makes it easier for users to have a strong passcode but maintain usability is definitely something which we'd like to see. Also, iOS and Android both added new security features and patching security vulnerabilities with each release, so it would be good to update to a new software version as much as possible. But we have seen that this is challenging, in particular for Android devices, and even iOS devices lose support after a while. And then for iOS, at least, there's remote wipe and wipe support. If you type in the passcode a number of times wrong or you lose your phone, you can wipe the device. So that would be something security-conscious user could enable.
And for the Android side, I think we've seen there's the need to choose your device wisely. I think you need to do a little bit of research in what you're buying to see what security precautions exist and how timely the updates are. Like if you're going to get something that doesn't get updated for 2 years, you're going to have problems. And also encrypt your user data partition. This is still an electable thing that you have to do. And even though we just sort of showed a demo how that's not always going to help you, it is at least another barrier to entry for someone who's after your data. And in terms of best practices for developers, as Daniel mentioned, determine if you actually have to store this data locally. If it's convenient and to cache it, but there's security trade-offs, like maybe think about that before making those decisions. And on Android, it's particularly hard to rely on the platform security in a lot of cases because, as I mentioned, you don't always have access to all the latest stuff in the version you're running. And something of a discussion point that any application developers want to chat with us afterwards is like, how do you guys handle supporting older versions of Android from a usability and security platform? So we'd love to hear how people are doing this out there.
Yeah, and on the iOS side, you want to definitely use some of the protection classes which are involving the passcode, which we've seen for file system and for keychain encryption. And then if there's a user who doesn't have a passcode set, which you can test using the keychain when passcode set operations and things like that, either you can refuse to store the passcode, or not the passcode, but to store the sensitive data on the device and just have the user log in every time, or you can warn them that it's less secure. So there's alternatives there. So just a brief outlook after talking about this. The main thing we see here is usability. And so for users, we need something which goes beyond passcodes. We cannot really expect them to have a very long passcode and type it like 100 times every day into their device. That's not a solution which is really acceptable. And biometrics go somewhat in the right direction with like fingerprints and things like that, but there's a lot of room to grow in that space and to develop those. And then for developers, we really would like to see consistency in the platform, that we don't have so many different versions and everything is not clearly documented, and we need to figure out sane defaults, that we don't have to guess on what is happening in the background and that accidentally something gets deleted like we've seen in the key store in the past.
So the takeaways that we'd like, if nothing else, for you to remember from our discussion here is that security controls should be balanced with the sensitivity of the data and the threat model in question. So protecting your Candy Crush score versus your company's financial records are two different problems and require different solutions. Secondly, protect data until access is actually needed. This is something we'd like to see. Keep things locked until you absolutely need it, so that it's just not fully open once you boot the device. And lastly, I think our demo demonstrated that secure storage relies on the entire stack being secured. And if that is not true, things like Rosie are possible. So some references for you to look at later. There's a lot of good information out there. And thanks everyone very much. And any questions we'd like to field.